thank you everyone for making it to the final session of Reinforce. Sean and I promise to make it worth your while. Earlier this year, we launched a new proven correct authorization engine for all of AWS. This is some of the most security critical and heavily used software in our cloud. It's called 1 billion times per second, and it's responsible for granting or denying access to every single API call. Our goal in this launch was for this new engine to match the previous one's behavior, call for call. Now, we worked hard to ensure this launch went well, but it went better than anyone expected. In fact, this launch was unnoticed by everyone, customers and our service teams alike. It just worked. An analogy that we like to use for this launch is that we changed the engine on an airplane while it was in flight, and the passengers didn't even notice that it had happened. So the question is, how did we change something so important and so heavily used without anyone noticing? And the answer is, we used automated reasoning. I'm Lucas Wagner, a senior applied scientist in AWS's identity organization, and with me today is Sean McLaughlin, a principal applied scientist on our team and the technical lead for this effort. Today, we're going to tell you about the journey that we took to launch this, how we built it, proved it correct, and validated our proofs on 1 quadrillion production authorizations to be absolutely sure that we got it right. So here's what we're going to cover today. First, we're going to talk a little bit about automated reasoning, the technology that was critical to this seamless launch, and how we proved AWS's authorization engine correct. Then we'll do a quick overview of IAM, its architecture, and how authorization works so you know exactly what we proved correct. Then Sean's going to take the stage, and he'll give you a deep dive on how we built, proved, and validated this engine was ready for launch. And then lastly, we'll wrap up with a quick segment on how you can get proven correct authorization with Cedar and Amazon verified permissions for your custom applications. And these two solutions incorporate the 15 years of lessons learned that we have from operating identity and access management. Let's go ahead and get started. So, what is automated reasoning? Automated reasoning is the use of algorithms to construct and audit proofs and mathematical logic. The way I like to think about it is automated reasoning is the application of proofs, the same approach to building proofs that you learned in high school geometry, scaled up with algorithms and tooling to enable reasoning about larger, complex digital systems. Before we get into the details of automated reasoning, let's take a step back and talk about why we want to build proofs. Proofs are foundational. Now, everybody's familiar with the Pythagorean theorem. This theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the square of the other two sides. Or, more succinctly stated, a squared plus b squared equals c squared. Once this was proven by Euclid in 300 BC, society was able to build and innovate around this newfound truth, using it as a mathematical building block to make advancements in architecture, construction, navigation, and also serve as a building block in larger, more complex mathematical proofs. Now, the proof of the Pythagorean theorem was on pencil and paper. First, you had to carefully document your assumptions, that you were reasoning about a right triangle. And then you built a set of proof steps, one step at a time until you were able to prove your target theorem, a squared plus b squared equals c squared. Now imagine using a pencil and paper for proving something about a large, complex, and constantly evolving artifact like a computer program. This is where automated reasoning comes in. Automated reasoning scales to build proofs of complex digital systems by using algorithms to assist the proof engineer in building and maintaining the proof as the system evolves. In the work that Sean's going to tell you all about, our proofs, on every commit to our proofs, we reran them and understood what was still true when a change occurred and what was no longer true and needed to be updated. Now, AWS has been investing in automated reasoning for the last 7 years, and we've applied it in several areas, but one way that I'm going to talk about today is the way we've applied proof to help our customers secure their S3 buckets from public access with our S3 block public access check. You can enable this check in the S3 console for a single S3 bucket or all the buckets in your account. Now, underlying this check is an automated reasoning algorithm that automatically builds a proof that your bucket is not publicly accessible. This is foundational. With this proof, you have greater confidence that your S3 buckets are secure, and a level of confidence that would otherwise be very difficult to replicate by any other means. Now, if you're curious about how we did this, how we generate these proofs, we've published a technical paper on it, and you can read about this and learn all the details. Now, the S3 block public access tool constructs proofs automatically using algorithms that are specific to IAM policies and the behaviors that they permit. Another common way to use automated reasoning is to construct a correctness proof over a foundational piece of computing infrastructure, such as a processor, an OS kernel, or a compiler. Now, these types of proofs are very difficult to automate, and so typically they require a large engineering effort with a dedicated team to manually build and maintain the proofs. But the payoffs can be very wide-reaching. Once a piece of computing infrastructure is proven to always uphold a key behavior, it can be readily used as a foundational building block in a larger, more complex system. Now, here are some peer-reviewed papers that are outlining large engineering efforts to build foundational proofs for computing infrastructure. On the left, my former colleagues at Rockwell Collins proved that a microprocessor was free from unintended communication across its partitions. This proof backed an NSA certification that a single AMP7G microprocessor could simultaneously process unclassified through top-secret code word data. This was the first certification of its type and the first processor allowed to do this. Now, on the top right, I'm showing you a paper written by a team at NICTA, an Australian government research organization. They built and proved correct the SEL4 OS kernel to show that it was free from the types of errors that would compromise operating system security. And in the bottom middle, I'm showing you a paper from INRIA, a French government research organization. This team built a proof that their C compiler's output always exhibits the same behavior as the input source code. So these proofs allow these computing components to be used as trusted building blocks in larger, more complex digital systems, and they can be trusted to always exhibit these key proving characteristics. IAM is the service that you use to specify who can access what in your AWS account. You, our customers, write policies to control access to your AWS resources. Now, authorization, determining if identity has access to a given resource, is done by evaluating incoming requests, 1 billion of them per second, against your policies. It's our job to enforce these policies correctly. Now, building a foundational proof that requests are evaluated against policies correctly gives you higher confidence that we got it right. Next, I'm going to do a very quick overview of IAM so you can better understand exactly which part of IAM that we've proven correct. So IAM is a large distributed system. It's available in every single region worldwide. It's helpful to think of it like a circulatory system. There are two major components: the policy management and distribution piece, and a runtime client library that every service incorporates into their API builds. And this runtime client library performs authentication and authorization. Now, policy management and distribution ensures the customer's identities and policies are quickly distributed all around the globe as they are created, updated, and deleted by you, our customers. Think of this like the veins and arteries of the circulatory system. So you create a policy or you update a policy. This is reflected in the control plane. Then through a propagation step, this information is distributed all across the world to all of our regions to ensure low latency in-region access for services in that region. As requests come into services, they process the request, and some information is passed to the runtime library, which contains the beating heart of identity and access management, the authorization engine. As authorization is done, it reaches out to the IAM data plane to fetch the most recent policies so that it can either allow or deny access. Now on the next slide, I'm going to dive into the second half or the bottom half of this diagram, and we'll talk a little bit more about what goes on in the runtime client library. So requests come into services. This is the inside of the client library. And as a request comes in, information is taken and passed to the client library. This information includes the caller making the request, the resource that the request is made against, the action that's trying to be performed, and then any other contextual information that might be relevant for authorization. Now, the identity and the resource are used to make a call to the data plane and fetch the policies that govern access to those identities and resources. Now, inside of this client library, as I told you, there's a beating heart, the authorization engine. And the authorization engine takes request as an input and checks it against these policies and determines whether or not the answer is allow or deny. If the answer is allow, the service is allowed to continue to do its work and return the appropriate response to the caller. And if the result is denied, an access deny result is given back to the caller. This beating heart is what we've proven correct. So you're probably asking yourself this question: why go to all this trouble? AWS has been operating successfully with the previous algorithm for the last 10 years. Why go to the trouble to build this foundational correctness proof? And there's two answers to this question. First, we're security obsessed. It's in our DNA to continually raise the bar for secure operation. This proof gives you greater confidence that we're correctly evaluating policies, because this proof applies to all possible inputs into the authorization engine. Second, we're customer obsessed. We want to continue to make changes to this very important algorithm, but we want to do it with more confidence and greater speed. Having proof available helps us convince ourselves that the changes we make do only what we expect and nothing else. At this point, I'm going to invite Sean up to the stage, and he's going to talk about the deep details of how we built this engine, how we proved it correct, and how we validated it. Here you go, Sean.
Great, thank you, Lucas. Well, I'm really excited to be here to talk about this project. I joined the automated reasoning team in AWS Identity around 4 years ago. And I went to my boss, like our first one-on-one, and I said, well, what should I work on? And she said, well, authorization is used all the time. Like, that's a really important foundational thing in identity. Why don't you take a look at that? So I got interested in the following question. So how can we be sure that we're evaluating policies correctly? And like, what does it even mean to evaluate them correctly? Like, what does correct mean? So I had worked at a startup. I was using AWS before I was an employee. I had been working with AWS as an employee, so I had a lot of experience. I'd written a ton of policies, but I was no expert. I was just like a user, and so I didn't know exactly how to approach the problem. So I went to the documentation to look around, and there's a page about how policies are evaluated, which many of you probably read, and I came to the following sentence. An explicit deny in any policy overrides any allows. So this kind of sentence is like catnip for an automated reasoning person, because what it's doing is it's making a statement about all possible inputs to something. So in this case, it's saying no matter what the policies are, no matter what the request is, if a deny statement matches, then the result's a deny. Later down on that page, it uses the word trumps. The deny statement trumps the allow statement. So let's try to write that down in logic. So first we'll start kind of use a logical pseudocode to try to flesh it out a little bit. So what does deny trumps allow actually mean? So I'm going to say for all policies and all requests, if there's a policy P in the set of policies you handed me, and a statement S that's in P, so I need to find a specific statement in this big bag of policies, that the statement has to be a deny, the S has to match the request. If all of those conditions are satisfied, then when you evaluate the request, the result is a deny. So this is a lot more wordy, right, than deny trumps allow, but this is something where we can actually start to think about it as a logical formula. So the way we're going to express logical formulas today and code of different kinds is in the Daphne programming language. So like Lucas was saying, we are doing proofs very similar to how Euclid did them, except the systems are so big, and we have to rerun them whenever we change it. It is unmanageable to do it by hand. And so we need to use software. So Daphne is a language, an open source language, where you can write specifications, implementations, do proofs of various sorts, all in the same ecosystem. So almost all the code I'm going to show you today is in Daphne. So this is that statement, deny trumps allow, in the Daphne programming language. I'm going to just step through it with you quickly. So first we're going to say lemma. We're going to tell Daphne we are doing theorem proving here. Give it a name. And then we're going to kind of walk through the English and convert that into logic that Daphne can understand, and then we can work with subsequently. So for all policies and requests, if, so there's a requires clause, that's the conditional. If there exists a policy P and a statement S, where the effect of S is a deny, and S matches the request, then there's an ensures clause. If all of the requires clause expressions are satisfied, then it ensures that when you evaluate the statement, you get a deny. So this is like, I mean, this is a kind of a deep statement about authorization, which is a pretty big algorithm, and it kind of fits on a slide, which is pretty cool. But what does evaluate mean? So now we have to tell Daphne about evaluation. Daphne by itself doesn't know anything about evaluation. So we're going to write something called a specification. We're going to try to explain to Daphne as succinctly as possible what evaluate means. And so we're going to work backwards. So I'm not going to think about performance. I'm not going to think about how I might write this efficiently. I'm just going to try to write it as clearly as I can. And so the algorithm I'm going to use for evaluate, I'm going to tell Daphne function is kind of like saying it's a specification. Give it a name. It takes the same arguments for the policies and the requests, gives an answer, implicit deny, explicit deny, or allow. I'm going to search through every single policy and every single statement looking for deny statements that match. If I find one, great. I'm going to deny it. Next, I'm going to go through that whole process again. I'm going to look through every policy, every statement, and look for an allow. And if I find one, great, then we allow. And otherwise, we implicitly deny. So this is like so simple, it's almost like, it almost doesn't make sense to write down. It's like so obvious. But that's kind of the point. We want someone to look at this and say, oh, this is obviously correct. This is obviously what we mean when we're talking about evaluation, policy evaluation. And of course, you would never implement this, right? So the engine that's running 1 billion times a day is not going to do this silly thing, because for one thing, we could optimize it. This algorithm, we could say, oh, well, while you're looking for deny statements, if you see an allow statement that matches, just remember that so I don't have to do the second step. So I've already halved the time of the algorithm. So obviously we're not going to run this, but it's for humans. We're going to try to specify this as succinctly as we can. But of course, we've just told Daphne what evaluate means, but we haven't told it what matches deny means. And to tell it what matches deny means, we have to tell it how to match a statement. And to tell it how to match a statement, we have to tell it how to match a condition. To tell it how to match a condition, we have to tell it how to do the lowest level things, like string matching while you ignore case. But at some level, you bottom out. You do the number stuff, you do the string stuff, and at the end, you have Daphne knows everything about the specification, and you've written it so simply that a person could look at it and say, ah, yes, this is what policy evaluation means. Now, one of my jobs today is what I would like to do is give you a feeling for what it's like to do automated reasoning at AWS. And so I'm going to give you I'm going to do every step from doing the specification and theorems all the way to running the code. But I'm just going to, because authorization is big, so I'm just going to take a really tiny example, part of authorization, which is just this string matching where you ignore case. And using this, I'm just going to try to give you a feel for what it's, what we do every day when we do automated reasoning. At least this type of automated reasoning. And I like to present this by using a development cycle. And so I call it the automated reasoning development cycle. And I'm going to compare and contrast it with the software engineering development cycle. So I was a software engineer for a long time before I started doing this kind of stuff. And what did I do as a software engineer? Well, there's a specification. So either I've written a design doc or someone has written a design doc for me. I've had an idea, it's in my head, I write it down on paper, I write it down in Microsoft Word, something like that. But I have an idea of the thing I want to build. So that's what we're going to call a specification in the software engineering development cycle. The next thing I do is implement it. I bust out my laptop and I start writing my Rust code or my TypeScript code. And then I test it. Did I do it right? So I have all these unit tests. If the unit tests fail, I go back to the implementation. If all the tests pass, but then I hand it to someone, they say, this doesn't do what I wanted, this isn't what the design was, well, maybe I go back to the specification, change the specification. And we do this in a cycle. And then at some point it evolves and you get to a place where the software is basically what you wanted and you're happy with it. We're going to do the exact same thing with automated reasoning. Some of the steps are the same, though the steps that are the same are a little bit more complicated than most of them. And there's a couple new steps. And I'm going to show you all of these steps in the context of this tiny example. So let's talk about case-insensitive string equality. So what is case-insensitive? Why do we care about case-insensitive string equality? Well, there's policy language features that require it. So subnets, for example, are not case-sensitive. You can write the subnet name in any case, and it refers to the same semantic object. And so if you look at the ELB documentation, it says, oh, make sure when you are talking about subnets, you use this operator. KMS and RDS have this in their docs. You can use tags that are case insensitive. Anyway, because policies can use it, we need to implement it. And what is it? It's very easy to understand. Lowercase Sean, uppercase Sean are the same. Capital Sean, mixed case Sean are the same. But Sean and my daughter Alice, we're not the same because S and A, no matter what the cases are, they don't line up. So, obvious, right? But things get a little bit harder. So there's languages that have symbols that we don't use in English. So this is a German SZ, I think it's called a double S. And so when you compare things case insensitively, you actually do want these to compare to the same thing. And this example is tricky because the S set is one character and the two S's is two characters. So this is already a little bit tricky. And then there's languages like Greek where capital sigma and lowercase sigma obviously should be compare insensitively, but there's some rule where if the capital sigma is the end of the word, it should be lowercase something else. So anyway, languages are complicated. That's just the point. But fortunately for us, the language problem has just been solved. I mean, people have been working on it for years, and there's a beautiful international standard called Unicode. My shirt. If anyone gets the joke, that's great. You're with me. So great, Unicode, it's 1,000 pages. It's a very complicated specification, but it solves this problem. So how does it solve it? There's a feature of Unicode called case folding. And you can think of folding just like lowercasing. Like take two strings, lowercase them, and compare them. Folding is like tiny technical differences. There's like 300 out of 150,000 characters are different than lowercase. Well, if you have that in your mind, that's basically what it is. So let's write the specification in Daphne for string equals ignore case using this Unicode spec. Well, the specification tells us you have to case fold them and they should be the same string. They should just be equal. So that's super easy to write down, the spec. Writing the definition of case fold is like more complicated. You have to handle all these these like unusual characters. But anyway, it's just some logic to write down that you kind of read out of a document. So we do that in Daphne, but of course, like we're just typing into an editor. We could have made a mistake. Like, how do we know we have the correct specification? So that's where the second step of the automated reasoning development cycle comes in. So we start proving theorems about the specification. And you could think of this as like essentially a test of the specification. Did I write down the thing I wanted to write down? And this is kind of an art. It's not necessarily a science. So did I get the right spec? Well, we can just think to ourselves, what are some things that should be true of case-insensitive string equality? Well, it should be transitive, right? If A and B are equal in this way, B and C are, then so should A and C be. So if this thing is not true, then we have not written down Unicode correctly. So in Daphne, what does this look like? We say for all strings, A, B, and C, if A and B and C are related, then A and C are related. And so this little Daphne can prove this without any help. There's little squiggles on the bottom, which I didn't highlight in red. But the reason I'm showing you this slide, even though this theorem is relatively simple, is A, like it's like a sanity check. Did we at least do something that makes sense? But B, it shows that Daphne didn't need any help proving this. And that's really important because as authorization, as the program you're trying to verify grows, it's helpful to not have to help the theorem prover every step of the way. You want like as much kind of automation as you can. And Daphne does a lot of this automation for us. But just because something's transitive doesn't, like, we haven't gotten very far. So what we can do is we can dig into the Unicode standard and look for like that catnip. Like what are some statements that should be true about case folding? So what we find somewhere in the doc is that a statement saying if you lowercase something, then, and those things are equal, then they should also be equal when you case fold them. So then we can do the same thing. If for all A and B, if the lowercase forms of A and B are the same, then they should, equals and sensitive should be true. They should fold to the same thing. And then, great, Daphne can do this. It takes a little bit of work, but Daphne can do it. And the really neat thing about Daphne is if you mess up, if we had done that implication in the wrong direction, then it would have, we couldn't have proved the theorem. And so Daphne is like, it's just guardrails for it's always watching you, making sure you're not messing up. Okay, so we have a nice specification handed to us essentially for string matching. We have theorems about it, so we have some confidence that the specification is right. We're not positive, but we have some confidence. So now let's implement it. And this is the thing that's actually going to run on your machine. So the specification was for humans, essentially, and the implementation is for the machine. So the first thing we'll try, we can also write this in Daphne, which is nice. Daphne just says method, so you just have some different syntax for things you want to execute. And the way we're going to implement it is we're just going to run the case fold on both and compare them for equality. So, I mean, they're so similar, it's almost impossible to distinguish them, but one of them runs and one of them is a specification. And how do we connect, the implementation to the specification? What you do is you add an ensures clause. You say, I'm going to name the result of my method call, and I'm going to say, Daphne, please prove that the result is always equal to this specification. And in this way, yes, sorry, I got it behind. It's always equal to the result of the specification. And so doing this, Daphne has no trouble proving they're the same because they look almost identical. So this is our implementation one. And what we're going to try to do now is do better, because this is really not fast. The reason it's not fast is, like I said, most strings are not equal. Like Sean and Alice are not equal. If you take two random strings out of the world, they're not going to be equal in this way. And so what our implementation does is it takes string 1, makes a copy, which is slightly different, and then it takes string 2, which is slightly different, makes a copy that's slightly different. And then it looks at the first characters and says, oh, this one's an S, this one's an A. Like, sorry, they're not equal. Like, hugely wasteful. And then the garbage collector has to run. It's like, not what you want. So how do we make this faster? Well, we'd like to go character by character, right? Because then we don't have to allocate a big string. We can just like walk down. So let's try this. And remember that we still have this ensures clause. So Daphne's going to be checking each step of the way that we're doing the right thing. So our second implementation, we're going to check to make sure the lengths are the same, because like if one's longer, then it doesn't make sense. And then we're going to just walk through. So we have two strings, and we're sort of walking through one by one, checking the characters. We're going to check. Of course, you have to check them at the characters are equal, like using this folding, but it's only a little bit complicated. And then you return false if they're different, and then you return true if you make it to the end. So great, fast, pretty obvious, like, and simple, and wrong. So why is it wrong? Well, Daphne won't necessarily tell you exactly why, but if you dig into the proof and you keep trying to prove it enough, you'll realize that there are these interesting characters like I showed you earlier, where one character on the left is equal to two characters on the right, which means that this could never work, right? You could never have a character by character comparison match. So let's try number 3. We'll try to improve on number 2. And again, Daphne's keeping an eye on us. We're going to look for unusual stuff first. We're going to like walk through both strings to see if like we're in the danger zone where something like this happens. And if we are, then we're just going to do the slow thing. But if we're not, we'll just go back to the character comparison that we showed earlier. So we can basically combine implementation 1 with implementation 2. We're only slow like every blue moon. And Daphne now can tell us, great, you're good. But can we do any better? Well, I think we can, because again, like you have two long strings, and probably there's nothing wrong with them, right? Probably they're ASCII. And just searching, you don't allocate anymore, but you're still searching from end to end. You're scanning the entire strings before you have this obvious difference. And so instead, what should we do? Well, we can first, we're going to lazily look for unusual characters. So we're going to use a pointer, but we have to be a little bit careful, because strings that are different lengths are allowed to be equal. And so I don't want to overrun one of my lists, because then you're worried about memory problems. So you want to Daphne will keep you from doing that, but just conceptually, you don't want to go off the end of any arrays. So we find the smallest length of the list. We're going to go character by character. And now we're going to look at that character. And if those are weird characters, then we're going to do the slow thing. And if not, then great. If they're not equal, we turn false. And then otherwise, we make it to the end. And there's a little subtle argument why you need the lengths to be the same. So we went from some a one-liner, and we got this kind of bigger implementation, and Daphne is proved it's correct. And this is a true story. So as I was writing these slides, I was thinking to myself, I'm going to convince them that this is this really fast algorithm. But I thought, well, wait a minute. Like, what if I've gone through most of the string, and then I see the unusual character? Well, implementation 4 goes back and does something slow over the whole thing. Maybe if I truncate the stuff I've seen already and trust that those are equal, just look at the suffix. I'm pretty sure that this is still true, but I'm not positive. I haven't tried it. But Daphne would help. If it's true, then Daphne, I'll be able to prove it with Daphne. So this is this is how we take little bits of code to like try to like aggressively optimize them. And the reason Daphne is so important in this process is that if I were to just tinker with the authorization algorithm like in production, like maybe I could convince people that this would be faster, but if there's a little mistake in it, then like we don't want to like give customers the wrong answer, right? So we would probably not do an optimization unless it was extremely valuable. So we'd probably not do this optimization. And Daphne like opens the door for many more such like aggressive optimizations. All right, so let's say now we have like the implementation we want. Well, Daphne, we don't run Daphne code. So how do we get code that we're actually going to run? Well, the first question is why not? Why not just run Daphne code? And the answer is that authorization isn't its own. It lives in an ecosystem of other languages, like so Java in particular. So authorization exists in this larger Java context, and so you have a JVM that's churning through the other steps, and then we get to authorization. We want to sort of stay in the same runtime, and plus we've been using Java for decades. Like we understand how to run it in production, and like we're not going to just take some new runtime without a lot of testing. So we want to get Java code out of our Daphne. And so we're going to compile. We're going to take that Daphne implementation and compile it to Java. Now, what do we want out of? I mean, it's a little bit weird to call it compilation because you're basically taking like a kind of a very high level language like Daphne, turning it into a high level language like Java. I call it compilation. Some people object to the term. So anyway, you call it translation, call it compilation. But either way, we want it like any other compiler, we want it to be correct. We want the semantics of the source language to be the same as the semantics that you get in the target language. That's obvious. And we would like the code to be fast. We would like to have the Java code we generate actually be efficient because we're going to be running it at a gigantic scale. And this is true of any compiler for any language you want. This is like obvious. But we also have another requirement of our compiler from Daphne to Java, and that's that the code be readable. And it's a bit of it's an unusual requirement of a compiler because normally you just run the compiled code. But in our case, we do other things besides run the compiled code. We code review the compiled code. Why do we code review it? Well, there's lots of Java programmers in AWS, certainly compared to the number of Daphne programmers, and lots of Java programmers that care about authorization. And they don't just care about that it does the right thing. They care about that it's efficient. They care about their tail latency. So they're really interested in this Java code when it's changed. So we want people to be able to see what we're doing. In debugging, so again, we're not the only users of authorization. If an engineer on S3 is debugging some weird behavior that he doesn't understand, then they're in their debugger. They would like to see, like, in your debugger, you want to see code that is nice looking and that you can make sense of in your head, as opposed to code that looks like it's generated by a compiler. So that was we decided early on that was going to be a requirement for a compiler from Daphne to Java. Now, Daphne has a built-in Java compiler, which has the first two features, but not the third. And this is that last implementation we saw. And what the output of the default Java compiler is. And while it's correct, and there's some things, you don't have to understand it, but let me just point out a couple of things about it. So the default one translates the types of things that you wouldn't probably want when you're interfacing with other code, like when you're programming. So we would like to have string as being the arguments, but this gets compiled by default to a Daphne sequence of code points. And this makes perfect sense to how Daphne works with strings in Unicode. But for us, we would prefer string for the readability aspect. And then there's a little smaller cosmetic things, like the original Daphne to calculate the smallest length of the two lists. The Java we wanted essentially just looks like the Daphne, like you would write by hand. And then the compiler generates a lot of text that you probably don't want to see when you're debugging. So, yeah, right. So our compiler takes a subset of Daphne and generates readable code. All right, so where were we? We started with the specification, we worked through implementation, now we have Java code. And now we have something we can run. And again, so the right-hand side of this picture is all Daphne, like this nice, beautiful, logical connections between everything. And on the left is reality. And so validation is really comparing this model that you've spent so much time on to the cold, harsh reality. So how do we do this in the case of case-insensitive string matching? Well, there's lots of things we can do still, right? So there's unit testing and fuzzing, like you would do like with any other piece of code. But we do want to connect it to reality. So like we can look at industry standards. So Unicode committee publishes like test cases for folding that we would probably want to make sure we pass. We could look at Python. So other languages, like Python has a nice Unicode library. We could like fuzz ours against the Python one and make sure if there's a difference, like we could go to the Unicode spec. So there's lots of ways to connect our string matcher to reality. And that's the process, right? So if we find that the Python version generates something different from ours and Python's correct, well, we go back, we fix our specification. Because again, remember, the implementation and the specification are the same. So we know our specification is wrong. It's not just the implementation. We fix our spec. We make sure the theorems are still true. If they're not, the spec's broken again. We need to fix it. And we do this cycle, and then hopefully that test passes the validation this time. And we iterate and iterate, just like we did as software engineers, until we're happy with what we have. OK, so that was for the small, like bottom piece of authorization. And now we're going to essentially just work our way up. From every leaf, we're going to kind of work our way up to the top. We do the same thing with condition matching, same thing with statement matching. And then we can sort of do our implementations for all of these different things. So evaluate, in particular, is going to look a lot different than our evaluate spec. It's going to be fast and fancy, but we're going to maintain that fact, those ensures clauses that connect the simple specification to this implementation, however complex it might be. And so let's we can take a look at what this looks like for the entire algorithm. Now that we've seen a small part, I'm going to give you like just a much higher level view with fewer details about like for the whole algorithm. So the specification we've already seen. The theorems we already saw, deny trumps allow. So we've done the same thing that we've done with our theorems down below and just brought them up, done bigger theorems. The implementation and translation pieces, like they're just bigger. They look the same, but they're just way too big to fit on a slide. But you know the entire methodology now, so like nothing would surprise you. But validation was hard. It was a lot harder than looking for some test cases in the Unicode archives. And again, I want to remind you that the validation is where we're connecting reality to this model. And so now, reality, kind of what reality is depends on the example at hand. And so for the full authorization algorithm, what do we have? So right now we have old Java code that's running in production happily for 10 years. We inferred the Daphne specification from it. We read some documentation, we read the Java code, and we came up with the specification. We did a nice implementation, we did proofs, and now we have this great new Java code. But what connection connects these two bits of Java code in reality? So there's nothing concrete. It's all like we looked at stuff and we tried to make it as close as we could. So there's like no logical connection between this old Java code and the new Java code. So we can't just like lob the new Java code into production. We really don't know. We have no idea like if it's different or not. So here's reality. And what are we going to do? Well, we're going to unit test. We're going to take all the existing code unit tests, make sure they pass. We're going to fuzz it. We spent over a year working on a fuzzer. It's tricky to write a fuzzer for this because you have to make the policies, but then you have to make the context, and the things have to match with some probability, and there's like a huge number of language pieces. So anyway, we spent a while. The fuzzer found tons of differences, but after a while, it became like it would never find anything, even if we ran it for days at a time. So fuzzing, at some point, as valuable as it was, ran out of steam. And so we took advantage of the fact that authorization just massively scaled. And we implemented something called shadow mode across AWS authorization. So how does shadow mode work? It's super simple. The customer sends a request. You run the old engine. You send them back the answer. Like if it's an allow, then you kind of keep doing the business logic of the service. If it's a deny, you deny. But you also run the new code, and you look for differences. If there's an allow-deny mismatch, you send a metric. If the new code is super slow compared to the old code, you send a metric. Like anything that looks interesting, we make metrics for. And so I at this point, from my initial meeting with my one-on-one with my new boss, this is probably like around 3 years later, I'd been looking at this code for 3 years. So I was like, there are going to be, I'll probably find some differences. I was humble. Like, there's going to be like 100 differences a day probably. And we'll find them. We'll like go through and find each one of those 100 examples. We'll debug them. So we shipped our code, and we found around 100 million mismatches per day. So this was surprising. Like, wow, it's a huge number, but it's actually a pretty small percentage. Like, I don't want to make us look too bad. It's still like really a small percentage, but it's a lot. So how do you debug 100 million mismatches? Well, you find one. You like look for one, and you figure out what the difference was, and you just kind of try to knock them off one by one. And so I want to give you an example of something that shadow mode found that we didn't find any other way. So that has to do with time. So in time in IAM policies is nice, right? You can say, I want Alice to have access until June 1st. And so when you look in the documentation, this slide just shows you how you can write down the date and the time, and it even goes out to the millisecond. I believe it can even go, the standard goes to microseconds even. So you can have super precise times in these policies. So there's like two input formats. You can have epoch time, which is seconds since 1970. And then you can have this ISO 8601, which is the time standard. And it's the time standard, ISO 8601, that's interesting. And so I believed that we didn't need precise times, like to the millisecond. This did not make sense to me logically. And so why is that? Remember this a slide that Lucas showed you earlier, how we have this big propagation system. So this propagation system takes seconds, like small numbers of seconds. Sometimes in the tail it can be, I think, over a minute, but it's not milliseconds, right? And so when we look at the code that handled the times, it was more complicated than I thought it needed to be. We have some data types were millisecond precision, some were second precision, like the Unix one or the epoch time. There was numbers, and like, how do you interpret the numbers? I had to look it up every time. Is this milliseconds? Is this seconds? No, like, let's just make it all seconds. This is great. We'll just truncate the milliseconds, and life will be better. We'll be simpler and faster. It'll be great. But obviously, I'm talking about it because it was a bug, and so it wasn't. So what was wrong? So my mental model of IAM did not account for session policy. I never used one. And if you haven't either, well, you're in good company. What a session policy is when you assume a role, you can sort of say, I want to scope it down. So you can only access S3, even if this identity has more permissions, they can only use S3. And the interesting thing about session policies is that those get like shoved in your credentials. So it doesn't live in this ecosystem in the green circle. It lives in your credentials. So while this takes seconds, this takes milliseconds. And so what customers were doing was awesome. They were testing IAM. They were saying, well, does this date stuff actually work? I'm going to like make a policy, I'm going to make a session policy, and I'm going to deny myself access in a half a second, I'm going to check to make sure access is denied. But then this causes differences, right? So I had to retreat, right? I gave up on my simplicity. We add the milliseconds back to the spec and do the whole cycle. Make sure the theorems pass, fix the implementation, and back. And we ended up, we fixed one bug. I actually don't know which bug the time one was, but our second edition, V1 of the engine had fewer, an order of magnitude fewer, but still a lot, right? And these shadow mode take a long time. You can see them ramping up slowly, and the reason is you're basically doing a code deployment to around 1 million-ish machines, and so like they're picking up as new machines pick up the new version of your shadow. You know, they're starting to issue these disagreements, and so you see it ramp up. But then we did the same process. We found a problem. There was a Unicode problem. We fixed that. There's like a number of them. And as the months went by, we like kind of ratcheting down. And eventually, by version 7, after around a year of this process, we got down to 0 disagreements. And we wanted to be really like cautious, so we ran 1 quadrillion samples with no differences. I had to check that was the name of the number because I don't think I'd ever said it in real life before. And then we were even more cautious. What we did was we didn't just make it the production engine, then we swapped who was shadow and who was production, because we thought, well, maybe if we had just looked a little bit longer, we would have found a difference. So we said, swap those things, and we still didn't see anything. And so we made the new formally verified authorization engine the production engine. So phew, that was like a long story, and we were really happy. And again, I want to get back to this question: why are we doing this? If we don't see any differences after all this time, like you've done like 4 years of work, what do you have to show for that? Well, this is our story before. We had reality, and we moved to new reality. And this is where we are in our story. But now, if we want to make another change, do we have to do another quadrillion samples? Like, it doesn't seem like we've necessarily bought anything, but we have. Because now we have a specification, and if we want to change something, we're going to have a new specification, and we can connect those things with proof. And so instead of just relying on, like looking at code and fuzzing and shadow mode, we can prove things about these 2 specifications. And so as we move forward, we believe that we'll be able to move a lot faster with change it. Like if we're going to do a new optimization or authorization, it will be we'll be a lot more nimble in the authorization space. Okay, so what about performance, right? We made a big deal, like, oh, we went through 5 versions of this string equals matcher. Did that have any impact? So when I started, and we were still just kind of thinking this thing through, I was chatting with some principal engineers, and I said, I've never run a big service. Like, if we do some really fancy automated reasoning authorization, like, can it be slower? And like, if so, how much? Because it might be like harder to make it verified, and then, do I have a little wiggle room? And I didn't get any. We never did this formally or anything, but like the consensus was, well, okay, if you're 5% slower, that's fine. If it's 10%, pushing it, but like try to stay below 10%, and we'll talk. So when we shipped our last version, we were 65% faster at all the sort of percentiles we care about. Again, a percentile, so a P99 is essentially like the 1% of, it's like the 1%, the slowest 1% of requests are like what are in the P99 numbers. So the interesting thing in this graph is not like the blue is the P50, so that's more requests. When you go from the pink to the blue, what you're starting to see is garbage collection. And so we made a big deal about the allocations in the string example, and that was real. Like we worked really hard to not allocate when we could, because one of the biggest sources of these like long tail latencies is garbage collection. And so we were able to eliminate a lot of allocations and anyway, made the code faster. And I just want to reiterate that I think we wouldn't have attempted a lot of the optimizations we did if we didn't have this backing of proof. And it generalizes. This isn't just one service. So here's 6 services we kind of took more or less by random to show you that we're not just cherry picking. Great. So now Lucas is going to come back and tell you how you can use formally verified authorization for your services.
So that's the story. That's how we flipped the switch and how we seamlessly replaced one of the most critical pieces of AWS infrastructure, the authorization engine, with a proven correct equivalent. This proof's foundational. It gives you greater confidence that your permissions are correctly enforced. Now I want to come back to this question, why? Because I think it's still a fair question to ask. Why did we go through all this effort to be perfectly faithful to IAM, down to the millisecond, as Sean showed you? Why not take the design principles and the lessons we learned from 15 years of building and scaling out IAM and use the automated reasoning development cycle to build a brand new foundation? And the answer is, we did that too. Last year at Inforce, we open sourced the Cedar authorization language. Cedar is a proven correct authorization language that you can use in your applications. IAM is all about AWS principles, AWS actions, and AWS resources, but Cedar is about you, your principles, your actions, and your resources. And we use the automated reasoning development cycle that you learned about today to develop Cedar, because we want it to be sure that you have proven correct authorization available at your disposal in your applications. Now, speaking of making it easier, we also launched Amazon Verified Permissions. The best way to think of this is Cedar as a service. If you remember back to the start of this talk, I told you that authorization was the beating heart of identity and access management. But there's an entire circulatory system responsible for making sure policies are managed correctly and that they show up at the right place at the right time. Amazon Verified Permissions gives you that system for Cedar. Now, before I go, I just want to reinforce a few concepts that we learned about today. First, we've launched a new proven correct authorization engine. This proof of correctness is foundational to the security of your cloud workloads. Second, automated reasoning was key to proving this correct and deploying it seamlessly. This technology enables our proofs to scale to complex digital artifacts like AWS authorization. Third, as Sean showed you, automated reasoning enabled performance. Our new authorization engine is 65% faster than its predecessor without changing its behavior. And we were able to do this because automated reasoning maintained correct behavior while we aggressively pursued optimizations. And finally, Cedar and Amazon Verified Permissions give you correct authorization that you can use in your applications. Thank you for coming.